Today we're starting a new portion of the course and one of my favorite parts of the course about operational amplifiers or opamps. Before we learn about opamps, we should first talk about what an amplifier is. Amplifier does not start with M, it starts with A. So the idea of an amplifier is it takes some small voltage and makes it bigger. So like we've seen, let's say we have an AC signal that we are inputting into some circuit, and maybe this is, plus or minus 0.1 volts. So it's a plus, it's a 0.1 volt amplitude. But we're going to use that somewhere else, and we would like it to be bigger, right? This is a small voltage difference. Maybe we're using this to, turn a light on and off or move a motor or something that needs more than that voltage. We would like to have that same signal, but bigger, right? Multiplied by some number. So plus and minus, plus or minus 10 volts, we'll say. So how can we make this signal bigger by a factor of 100? Well, we put it into an amplifier. So the symbol, the generic symbol for amplifier is a triangle pointing to the right, an empty triangle pointing to the right. And depending on what type of amplifier, there might be different symbols to put in here. But the most important amplifier parameter to start with is the gain of the amplifier. So we've already talked about gain in terms of filters, and just like for filters, the gain of an amplifier is equal to the output over the input. So if we wanted to go from 0.1 volts to 10 volts, we would need a gain of 100. So we need an amplifier here with a gain of 100, and that would convert this 0.1 volt signal into this 10 volt signal. It's, essentially multiplying every voltage data point on this curve by a factor of 100. We can also express amplifier gain in decibels, and the equation for converting to decibels is still exactly the same. It's the 20 times the log of that same voltage ratio. So we've seen that before. Okay, so this is the idea of an amplifier. There are lots of different ways of constructing amplifiers, and we will we can construct amplifiers with transistors. They're more difficult to analyze. We do know enough to analyze them with things we've already learned, but it turns out that's not, in my opinion, that's not the best use of time in this class. So we're going to focus on a better way to make amplifiers, and really, if I were going to need an amplifier in a circuit, I would use opamps, which is why we're going to talk about opamps. Okay, so operational amplifiers. Sometimes it's written as one word, sometimes it's written as two words. So operational here means that these amplifiers, when they were originally developed in the mid-20th century, they were designed for performing mathematical operations in circuits. So you have two voltages, you want to add those voltages together, or you have two voltages, you want to multiply them together, or something like that. For those mathematical operations, they designed these amplifiers as components to use in that, and they've stuck around. They're very useful. So the anatomy of an operational amplifier looks like this. It is a triangle because it uses the general amplifier signal or symbol. What's different about this is it has two inputs, and one of these is labeled plus and one of these is labeled minus. So this symbol right here is sometimes just used for any sort of differential amplifier. So differential amplifier meaning an amplifier, like we talked about, it makes the signal bigger, but the input isn't just one voltage, it's like the difference of those two voltages. So the op-amps do fall into this class of differential amplifier. What it outputs depends on the difference between what's going on here, and we'll talk about how that is. Okay, so there are two inputs. The input on the minus symbol is called the inverting input, and the symbol with the plus is the non-inverting input. The output is just called the output. And the output, the equation that determines what's going on at the output is the output voltage is equal to the difference between the two input voltages times the gain. And this is the gain of this component is really more appropriately called the open loop gain for reasons we will see in a little bit. So this is the open loop gain. So this delta V between the inputs, that is the non-inverting input minus the inverting input. So that is V, we'll call that V plus minus V minus. So if this is higher than this, if the non-inverting is higher than the inverting, it will output a positive voltage. If the inverting is higher than the non-inverting, it will output a negative voltage. If they are the same, if they are exactly the same for an ideal op amp, it will output 0. This is uncommon to do in practice, and we'll see why that is. Okay, so now we're getting to the big important bit. This gain, this open loop gain, is really big. Really big. Typical open loop gains at low kind of kilohertz frequencies might be 10 to the 5th to 10 to the 6th, so 100,000 to 1,000,000. And of course, this depends on the particular op amps you buy and so on. It also decreases with frequency, so at higher frequencies this isn't as big, but at the kinds of frequencies we'll be doing, well, the kinds of frequencies we typically do in labs, that's where the open loop gain number is. So this open loop gain value changes a little bit with temperature, but in general it stays in this ballpark. It stays high. So it's kind of like, this value might kind of be thought of like beta of the transistor in a way. The exact value is going to vary from sample to sample, but you can at least know that it's going to be a big number in that order of magnitude. Okay. So here's where things get weird, because this gain is so big. Any tiny difference between the inverting and non-inverting inputs is going to make the output go crazy. So crazy meaning a really large magnitude of voltage. So if So there's one other piece of information we need, and that is our op amps are getting power from something else. So op amps need a power supply to operate, like most amplifiers, and sometimes those are drawn on schematics, sometimes they're not. And there are different names for these, but we'll call these plus V power and minus V power. Sometimes they're called V plus and V minus, but then that gets confused with the V on the minus and plus inputs, so we'll call them those. So the limits of this op amp, we'll get to that in a second. Okay, so a real op amp has these voltage inputs that it gets for its source of power. Okay, so for this ideal op amp, it has the following properties. For an ideal perfect op amp, the gain is actually infinite, or very, very, very big. Our input impedance, that is how much resistance this voltage feels to ground, or that's another way of saying that is how much this input wants to get current from whatever the source is. The input impedance is ideally also infinite, which means these inputs draw no current whatsoever. They are the ideal voltage measurement between those 2 points. And the output impedance is 0, meaning the output can supply as much current as is needed to keep this voltage at whatever it's supposed to be. Real op amp values, and these are typical values you can buy specialty op amps that are better at one of these or another. Typical values might be the gain, like I said, 10 to the fifth to 10 to the sixth. The input impedance is 10 to the sixth to 10 to the ninth ohms. So a mega ohm to a giga ohm. And this definitely depends on things like frequency and temperature, and definitely depends on what flavor of op amp you buy. So if you care about tiny input currents, that might be something to care about. But even a mega ohm at the input is, for our purposes, so much lower than any other resistances we're likely to be using. Whatever current is flowing in this input is not going to change anything over here. Or at least it's very unlikely to. Yeah, okay. And the output impedance is low, and it depends here exactly. What I mean by low depends on what op amp and what it's outputting, but certainly the op amps that we'll be using can source many milliamps of current, maybe 25 milliamps of current at 10 volts. So you can figure out what what resistance that's going to be. Some tens or maybe low hundreds of ohms or something like that. Low ohms, but not zero. So there is a limit. All this is saying is there is a limit to how much current the op amp can supply, and that shouldn't be surprising. Yeah. All right. Great. So the actual output cannot be at any voltage. The other thing that real op amps have limiting is the output is limited by the amplifier supply voltage. Meaning for most op amps, the output can only go between these two things that are powering the op amp. So very commonly, these two are plus and minus 15 volts. Those are very common values that we use in the lab, but other labs also use. So the output of an op amp here ideally would be limited between plus and minus 15, but even that doesn't happen because of how the op amps are designed. So most cheap op amps only can get within a couple volts of that. So like 13.5 volts or something like that are typical limits on the output. You can buy fancy op amps called rail-to-rail op amps that can go all the way to the negative power supply and positive power supply voltage. And they, cost a little bit more money or whatever. So we don't use them if we don't have to. So the output can only the output has to stay between those two supply voltages. All right. So next we're going to look at a little example of a very, very simple op amp circuit.